In this video, we are going to discuss about the principle of operation of a transformer and hence derive the EMF equation of a transformer. So from this magnetic circuit, you can see we have the secondary windings and the primary windings. Then you have an AC supply of V1 and V2. And then you have a flux linkage in this magnetic circuit. Then we have a current 1 and current 2. Then we have the load. So to start off, when the secondary is an open circuit, this is the secondary part of the magnetic circuit, and an alternating voltage of V1 applied to the primary windings, a small current flows, which is a no load current, which sets up a magnetic flux in the coil. It sets up a magnetic flux in the coil. This alternating flux with both primary and secondary coils induces in them the EMFs of E1 and E2. We have an induction induced EMF of E1 and E2. These are the EMF induced in the coil by mutual induction. That is the EMFs E1 and E2 induced EMF in this primary and secondary coils. Then the induced EMF E in a coil, in a coil of n turns, is given by, so you have an EMF E and then the number of turns n. So this one is represented by that E is equals to the negative of n, the d of that, the differential equation of a flux with respect to time. This is when you have a differential equation of that, of dt. This is called the rate of change of flux. The rate of change of flux. That is what we call the differential equation of d to respect to time. So in an ideal transformer, the rate of change of flux is the same for both primary and secondary coils. The rate of change is the same. So you have on the primary side, you have an EMF. We add E1 over N1, this is the number of turns in the primary side, is equal to the induced EMF on the secondary side with respect to the number of turns on the secondary side. So that is the induced EMF pattern is constant. Assuming no losses in the transformer, you have EMF E1 equal to V1 and E2, that is the EMF, the induced EMF E2 is equals to V2. Therefore, you have a V1 to represent the two equations. You have to replace in equation 1. Let's name this your equation 1. So when you replace V1 and V2 in equation 1, you have V1 over N1 equal to V2 over N2. That is when you replace E2 and E1 on your equation 1. So, or you can have a V1 over V2 equal to N1 over N2 So when you have a V1 over V2 is called the voltage ratio, and N1 over N2 is called the turns ratio. N1 over N2 is called the turns ratio or the transformer ratio, the transformation ratio, represented by the transformation ratio sometimes is denoted by the letter K. N1 over N2 is equals to K, and transformation ratio. So when a load is connected across the secondary winding, a current of I2 flows. So you have this one on the second, you have I2. This is the current which we are saying. When you have that, the current which we are saying I2 flows in that circuit in the secondary winding. So in an ideal transformer, losses are neglected, and therefore a transformer is considered to be 100% efficient. When the transformer losses are neglected, the transformer is considered to be 100% efficient. Therefore, the input power is equals to the output power. When you say power is equals to I squared R or VI. That is how you find power. But in this case, we are going to use the voltage and the current. Therefore, power is equals to VI. On the primary side, we have V1 multiplied by current 1, which is equals to V2 multiplied by I2 on the secondary side, which is equals to the input power. This is the input power on the primary side and the output power on the secondary side. Therefore, an ideal transformer, the primary and secondary volt amperes are equal. Volt amperes are equal. Volt amperes are equal. That is VI, they are equal. Therefore, V1 over V2 is equals to I2 over I1. Therefore, replacing that in our equation, let's say this is our equation 2. Let's call that our equation 2. Therefore, our V1 over V2 is equals to N1 over N2, which is equals to I2 over I1, which is equals to I2 over I1. I2 over I1. Moving on to the next, we have that after finding the operation of after explaining the working of a transformer, the principle of operation of a transformer, we derive the EMF equation of the transformer. Therefore, to start with, an alternating or a sinusoidal voltage applied to the primary windings of a transformer sets up an alternating flux in the core. That one we saw in the first explanation. Therefore, you let the phi m to be the maximum value. Phi m, this is the maximum value of flux. And f be the frequency. You have phi m to be the maximum flux, and then f to be the frequency. And then the time for one cycle is equals to, that's how you find time, that is the period. It's one divided by the frequency, and then the answer in seconds. That is how you find time, or the period. Therefore, when the flux rises sinusoidally from 0 to a maximum value in a quarter cycle, the time for a quarter cycle is equals to, when you have in a quarter cycle, you have the time now becomes a quarter of the frequency in seconds as the units. Therefore, the rate of change of flux is equals to phi m divided by a quarter of that. This is the same as phi m divided by 0.25 f, which is equals to, this one will be equal to, after you solve that, it gives you 4f phi m webers per second. That is the unit for flux. The rate of change of flux gives you webers per second. And since 1 Weber per second is equals to 1 volt, 1 Weber per second is equal to 1 volt. Therefore, the average EMF induced in each turn is equals to 4 multiplied by the frequency, then the maximum flux in volts. So as the flux varies sinusoidally, then a sinusoidal EMF will be induced in each turn of both primary and secondary windings. For a sine wave form factor, the form factor is equals to the RMS value over the average value, which is equals to 1.11. That is the form factor, the RMS. When you are given the RMS value divided by the average value, we get the form factor. Therefore, the RMS value is equals to to find the RMS value, it will be 1.11, which is the form factor, you multiply by the average value. Thus, the RMS induced in each turn, that's the EMF induced in each turn, is equals to, in each turn now, we had pattern, we had 4 pattern, we had 4 multiplied by the frequency phi m, that is in volts, that is per turn. Per turn we had that. Then now to find the RMS value, the RMS EMF, now it will be equal to the form factor you multiply by each turn. Each turn is equals to 4f phi m. That is the value of the RMS induced. Therefore, this one will give you a 4.44 by 4 FM. That is the EMF induced in the RMS value of the induced EMF. Therefore, the RMS of the induced EMF in the primary windings. The primary windings, you had the EMF. This is the primary, and then the secondary we had E2 in the secondary. But now the RMS of the induced EMF, now you have E1, you have E1, you have E1, you have E1 there, you have E1, which gives you that value. And then the RMS of EMF induced in the secondary windings is equals to that. Now you represent the number of turns with N2, which is the number of turns in the secondary side, and the number of turns is equals to that. So now we have learned that to find the form factor, you have the form factor is equal to the RMS value divided by the average value. That is how you find the form factor, and is equals to 1.11. That is the form factor. And to find the induced EMF on the primary side, E1 is equals to 4.4, which is the induced EMF per turn, F of flux. Now N1 being the number of turns on the primary, then you find the induced EMF on the secondary side, which gives you the RMS value of the induced EMF per turn. Now on the secondary side, you have N turns. Now this one becomes the EMF on the primary,